Hello and welcome to this lesson about simplifying radical expressions. The learning target of this video is being able to write radical expressions in their simplest form. Now before we get into all of that, I just want to cover some of the basics. There are a few things that we need to understand about radicals. The first one is this rule, that if we have two numbers being multiplied together under a radical, a times b, if we want to, we can break it up as the square root of a times the square root of b. Now this is useful for many things. One, this allows us to simplify when we are going this way. We take a big number and we reduce it to smaller numbers, and the goal is to maybe let a be a perfect square so that way you get rid of some of the radicals. But you could also go the other way. You can go from the right to the left. If you're multiplying two numbers under a radical, you can make it one bigger radical, if that makes sense. The second basic rule is that the same thing applies for fractions. So if we have the square root of a over b, we can focus on the square root of a over the square root of b to help simplify it. So that's fair game to do as well. And then the third thing is sort of a little catchphrase I like to say when it comes for radicals. And that is you have to have 2 under to get 1 out. And so 2 under, 1 out. That's what we have to remember. You have to have two identical factors, and when you take it out from underneath the radical, it becomes 1. It's sort of like a weird magic trick type thing. So that's the basics. Now, let's address the question that I'm sure a lot of you care about. When am I done? When have I simplified enough? This is something students ask all the time. So first thing is that there are no more perfect squares under the radical, that is. So what that means is you don't have a factor of 4. You don't have a factor of 81. You don't have a factor of x squared or of y squared or anything like that. All of these have been extracted out of the radical. The second thing is when there are no radicals in your denominator. So if you're dealing with fractions, you cannot have any radicals in the denominator. It's just not cool. All right, so that's the two criteria you need. You want to extract all the perfect squares, whether it be in numbers or variables, and you can't have any radicals in your denominators. Oh, I misspelled denominators. Denominators. There we go. Good catch. All right, so let's look at some examples of how to simplify. Let's take something like the square root of 96. This is a great example because we have, it's a big number, and we have a lot of options for how we can go about it. So we can do some work on the side. And the fail-safe for this is just to be like, all right, you know what? I'm going to break this down. I'm going to take out a 3. And when I do that, let's see here, that would be 32. Break down 32, that's 4 times 8, and this is 4 times 2. And at this point, we're kind of good. We can stop because 3 can't break down any further, 2 can't be broken down any further, and we've found two identical factors. And what we can do is say the square root of 96 is equal to 4 times 4 times 3 times 2. And that whole thing about having 2 under, 1 out applies right now. You take out the 2 4s, but only one of them comes out. So you get 4 square root, and then whatever's left underneath, which is 3 times 2, and that's 6. So that's one way you can simplify a radical. Second way is to know some of the factors of it, and maybe just try to go straight to the biggest perfect square. So it's more of an obscure factor of 96, but it's 6 times 16. Well, 16 is a perfect square. And so I could say, you know, instead of saying square root of 96, I'll say 16 times 6. And then I can just take the 16 out as 4 root 6. So multiple ways to get to the answer. Do what works best for you. Now the same principle, it applies to variables. So let's say we have the square root of 32, x to the third, y to the fourth. What you're going to do is focus on the numbers and the variables separately. So we'll take the square root. 32, that is 16 times 2. Again, I broke it down like that because I know 16 is a perfect square, and I can extract that out as a 4. What I'm going to do next is focus on my variables, and I'm going to expand them. So I'm going to take x to the cubed, and I'm going to write out all those x's. I'm going to write out all the y's, all 4 of them, because this visually helps me see what it is I can extract. 2 under to get 1 out. So I can take out 1x and 2 sets of y's. And what that leaves me with is, so we'll go to the final answer now, 4. One of these x's, and then I have 1 set of y's, and then a second set of y's, so I'll write that as y squared, times the square root of 2x. Box it, walk away. So that's starting off with something big like this right here and trying to take some numbers outside. We could go the other way around, where we have something like maybe the square root of 3 times the square root of 15. And so if we go back a couple of slides here, the basics, remember I can go either way with this rule. And so now I'm going to go from right to left. I can multiply these two numbers together. And when I do that, it might help to break down my 15 as 3 times 5. So that way I can realize I have 2 3's, and I can pull one of them out, and I have 3 root 5 as an answer. Next, let's put some numbers on the inside and on the outside. So let's say we're looking at something like 3 root 8 times 2 root 2. Now the point of this example is to talk about what can be multiplied and what can't be multiplied. This 3 and 2 can be multiplied. This 8 and 2 can be multiplied, but they do not interact unless you've reduced a square root. So I will get 6 times the square root of 16. Square root of 16 becomes 4. So I get 6 times 4, and that gives me 24. So sometimes when you're simplifying radicals, you may eliminate the square root over or completely from the problem. So now let's talk about a fraction. Now we're looking at the square root of 35 over 15. So first, I'm going to address what's going on in the fraction. I can simplify some things to make my life easier. 35 over 15 becomes the square root of 7 over 3. Take out that common factor of 5. Now, we're coming across a really important phrase, and it's a bit of a tedious task, and a fair warning with that, and it's called rationalizing the denominator. Rationalizing the denominator. What that means is we want to get rid of the square root, the radical in the denominator. So we can use the rule where I break up the numerator and the denominator like that. This is a big no-no. You're not allowed to have a radical in the denominator. Now, you might be wondering why. I don't have a good answer for that. But what I do have is it's not that hard to get rid of it. So what we just do is we multiply by what's down there as a 1. So you go square root of 3 over square root of 3. And what happens is these two square roots of 3 become just 3. So we'll have a square root of 7 times the square root of 3. We'll talk about that in a minute. Over, and then again, these two cancel each other, kind of cancel each other out. They cancel out the square root to get you just 3. Now you have to be careful. This 3 and this 3 cannot be crossed out because one's under a radical, one is not. You cannot reduce them. So the final answer is just going to be the square root of 21 over 3. Now, we kick this up a notch and we get another vocab term that we'll have to go over. And so here's what it looks like when we make things a little more complicated. So we now have an expression, 7 over 3 minus the square root of 7, where our denominator is an expression. 3 minus square root of 7. So in order to simplify this, what we need to use, it's called the conjugate. And the conjugate essentially is what will rationalize the denominator when you have an expression, and it's same numbers, different sign. Same numbers, different sign. So what we're going to do is to get rid of this part right here, I'm going to use 3 square root of 7, but the conjugate, I change the sign in the middle. And so it becomes 3 plus the square root of 7. And if I'm doing this to the denominator, I have to do this to the numerator as well. Now I get a foiling problem. So I'm going to distribute this to those two terms, and that will give me 21 plus 7 square root 7 over, and then I'm going to FOIL this. So I'm going to get 9. And then the reason why we have to use conjugates is they cancel out the middle term. So actually it's a shortcut. This will cancel, these cancel out because you'll get not negative 21, negative 3 root 7 plus 3 root 7. They cancel each other out. And then you're going to get, when you multiply the last terms, negative 7. Because the square root of 7 times the square root of 7 is just 7. Now it's about simplifying what we have. So take it one step at a time. The numerator stays as is. 21 plus 7 root 7 over 9 minus 7, 2. And that's as far as we can take it, because in our denominator there are no radicals. In here, there are no perfect squares. 7 is not a perfect square. You're done with that. And so that is how you rationalize the denominator when you have a more complicated expression down there. So that is in a nutshell how to simplify radical expressions. If you have any questions, please reach out to me and let me know, and I'll help you the best I can. Good luck.